antibiotic can be developed from their research part. But first, let's remind ourselves, I guess you already reminded this very nicely from the previous topics which I could hear, and previous the research which people try to present on this conference, but still they're antimicrobial agents. It's basically the components that treat their infection caused by different microorganisms. And in today's lecture, I would like to talk about antibiotics specifically, and antibiotics are antimicrobial agents which specifically used to treat the bacterial infection. And a bit of the history overview. I believe many of you know that penicillin was discovered in 1928 by Alexander Fleming, but basically he was not the one who discovered the penicillin. It was his PhD student, I believe, who left their plates with Staphylococcus aureus for too long, agar plates, in, I don't know, incubator or in the open space, that this plate was infected or contaminated with fungi. And he noticed after the fungi contamination, the bacterial growth was much more inhibited. And basically this was the fungi which was producing the penicillin compound. And further, when this compound was purified and nicely cleaned up, let's say, they got the penicillin, the pure penicillin, which further was used as antibiotic. And basically their penicillin discovery was one of the crucial ones, because it was helped many soldiers during the Second World War II not to die because of different wounds and bacterial infection. But as you can see on this timeline, oh sorry, I will put the laser point, beautiful. So as you can see, soon after the penicillin was discovered, like a decade later, the penicillin resistant bacteria was already identified. And the golden era for the antibiotic discovery was 50s and 60s of the last century. It when the most classes of the antibiotics was discovered, and soon after the most classes of the antibiotic resistant bacteria was discovered as well. And we are right now in, let's say, dark age, when we have more resistant bacteria than there exist in the antibiotic compound itself. But still we should not be very sad about it, because there is a room for improvement. So the most classes of their antibiotic are represented here, and the most superior class, it's of course their classes of the antibiotic which produced by other natural product, you can say. It's some antibiotics can be produced by fungi, some antibiotic can be produced by other bacteria, and only small class of antibiotics are actually synthetic or semi-synthetic antibiotic. And we would focus in today's lecture on their lincosamides class of their antibiotic specifically. I will explain you later why. So, but I believe this was already discussed in the previous lectures, which you hear today. It's how antibiotic affect their bacteria. So what they make, what within their antibiotic would make bacteria die or stop growth temporarily. So several antibiotics, including penicillin, they inhibit the cell wall synthesis. There's also a lot of antibiotic which inhibit their translation within the bacteria cell. So they bind the ribosome itself, 50th subunit or 30th subunits, depends from the antibiotic, and then they inhibit the translational mechanism, so bacteria cannot produce protein anymore, and it also dies. There is different antibiotic which inhibit their replication or transcription as well in the bacteria cell. So scientists are like smart people. They try to help and develop antibiotic which would target each and every process within the bacteria cell, so thus the bacteria would die or at least inhibit the growth and the patient can be treated. But bacteria is also alive, so it's evolving organisms by its nature. So bacteria develop several the mechanisms how to prevent the antibiotic to be able to kill the bacteria. Most of these mechanisms encoded within bacterial plasmid DNA or within its chromosome itself. So bacteria encode the genes, and when the genes become translated, right, they translate it rather in their enzymes, which can degrade their antibiotic itself. And in the previous lecture, the girls very nicely talked about their mechanisms of the antibiotic resistance. So here it's maybe like summary slide which summarize all of this process within one poor bacteria cell. So not so poor, but yeah. So bacteria can produce antibiotic degrading enzymes. Bacteria can produce the enzymes which would modify the target of the antibiotic. For example, if we know penicillin is targeting cell wall, so it will produce the special enzyme which would modify, like, let's say, receptors on the cell wall, and then antibiotic cannot recognize cell wall anymore and cannot degrade it accordingly. Also, it can produce the special efflux pump, which would just pump out their antibiotic outside of the cell wall. It can also modify the drug target. So, for example, if antibiotic targets special, like several antibiotic can target special genes within the chromosome, it will modify it, metylate it, or like alter it in some way that antibiotic cannot recognize it anymore. So, and one of their stuff which was studied in my previous group where I worked, I'm actually, I didn't introduce myself. Sorry, I will do it in the middle of the lecture. I got my PhD degree from Tartu University, and like for over 5-6 years, I worked in the institute, in the academia in general. Now I switched to the industry and we working on the antibody discovery, but before I worked in the group where we developed antibiotics. So and it's like our previous research, which I'm trying to show today on this lecture. So basically, we studied their antibiotic resistant factor or ABCF factor, which were produced in the bacterial cell, and they basically altered their translation inhibiting antibiotics. So their groups like lincosamides antibiotics, lincomycin, clindamycin, several groups of like macrolides antibiotic, they are targeting 50S ribosomal subunit. So they inhibit the process when their peptide chain, like amino acid chain, won't be produced during translation anymore, and the translation will be interrupted and stopped. So they target specifically this region in the ribosome, and basically the ABCF resistant factor altered this region in this way that antibiotic cannot bind anymore, but the translation still can be resumed and continued. Basically, our collaborator from Harvard University, they developed the new synthetic antibiotic, which is called iboxamycin. It's not yet in the market, but I believe right now it's in the step of the FDA approval. So this iboxamycin is derivative from clindamycin, and clindamycin is derivative from lincomycin. So it's like a long derivative from the lincosamide antibiotic. Basically, the main difference that iboxyl group is switched from their like N-terminal position to the C-terminal position, and such change in their chemical group of the antibiotic compound hopefully could improve their antibiotic property. And how it could do that in the way that if we have previously several antibiotics could not bind tighter to the 50S ribosomal subunit and could not inhibit translation very nicely. This modification, this chemical modification, which I showed just right here, makes antibiotic to bind tighter to their position in the ribosome where their elongation of the polypeptide chain happening. So antibiotic binds tighter and thus inhibiting the whole translational process in general. And the next step was to test that if this antibiotic is indeed better than the others. And in the previous lecture, the girls was talking about the MIC experiment, minimal inhibitory concentrational or минимальная инхибиторная концентрация test. They were talking about that. So this was done for the several species and several strains of the bacteria, which is usually present as a clinical isolate strain. So they will isolated from the sick patient as the classical strain from the collections. And you can see when it tested with the clindamycin against clindamycin antibiotic, their minimal inhibitory concentration, it's shown here in microgram per milliliter, I believe. But in the main point, the concentration, the minimal concentration which required to inhibit the bacterial growth is much more higher with the clindamycin or other like antibiotics than with the new developed iboxamycin antibiotic. As you can see, the concentration here is much more lower. But what our other colleagues didn't test, they didn't test it against the Listeria strain. And in the group where I used to work before, we have a collaborator who were studying the Listeria monocytogenes strains in general, because this is a very pathogenic strain. It causes this listeriosis for their like human organisms, and more importantly, it can cause their how it's to say, like if the woman is pregnant, it will cause the woman can lose the baby if she got listeriosis in her first trimester of the pregnancy. So it's very, very dangerous disease, and we decided to test, can this new antibiotic also help with the listeriosis? And indeed it can. So you can see here that we tested against several Listeria strains, and one of the strain which also had their knockout, like removed factor of this ABCF resistance factors, which we discussed before, which like mimic their binding position in the ribosome, like this one, and thus the antibiotic cannot bind anymore. So we tested against those factors as well, and as you can see in general, this new antibiotics really shows much more sensitive to the bacteria much more sensitive towards this new antibiotic there when the bacteria present in this original form, in the form when this factor is removed, and even when the factor is overexpressed, like in other species, like in Bacillus subtilis species, they have their own ABCF factors, this factor which cannot in the ribosome, which mimic their binding site, and their antibody would not inhibit the translation. Other bacteria has it as well, and as you can see, when this factor is overexpressed, so when you have a lot of these factor molecules present in the bacteria cell, the iboxamycin still bacteria more sensitive towards it than towards the previous classical antibiotic like lincomycin and clindamycin as well. So it proves to be sensitive, which is good. The next experiment which we decided to test is to determine whether this antibiotic is bacteriostatic or bactericidal. What bactericidal means, it means that antibiotic will kill the bacteria, and bacteriostatic means that it will just inhibit its growth, but some bacteria may still remain in their like organisms and still be alive, let's say, but just cannot grow anymore. So to be able to do that, you basically incubate their antibiotic with the bacterial culture for up to like 24, 48 hours, and then you just do their plate bacteria cells on their gar plate and count the colonies. And we did that. And as you can see, after 24 hours, their iboxamycin antibiotic shown in this blue line, you can see that bacterial growth is inhibited indeed, and even not inhibited, it started to decline, where the more classical antibiotics like clindamycin and lincomycin, you can see that the growth just like stopped. So clindamycin and lincomycin was clearly bacteriostatic antibiotic, while iboxamycin proved to be bactericidal. But since we tested against the listeria strains, and listeria grows much more slower than E. coli, we like 24 hours was not enough for us. We need to test it 48 hours after antibiotic present within the bacteria as well. And as you can see, unfortunately, for listeria strain, after 48 hours of the presence of their antibiotic in the culture, you could see that indeed it showed to be more static effect, the same as their clindamycin and lincomycin as well. But nevertheless, the bacteria is still more sensitive towards the new antibiotic. And the next step was to test post-antibiotic effect. This is where you incubate for 2 hours with their antibiotic present in the media. Then you remove the antibiotic from the media and you see how fast bacteria can recover, it grows back, right? And this is very important to know this information if you especially want to use this for the patient treatment in the future, because when we stop giving the patient the antibiotic, we need to know, like, okay, if there's some resided bacteria left, how fast it can start to grow back and reinfect the patient. So, and we did that. And as you can see, in general, we tested against different listeria species, but as you can see, in general, their bacteria recover, it grows back much more slower with their iboxamycin antibiotic present initially than with lincomycin and clindamycin. So their iboxamycin indeed has the strongest post-antibiotic effect among all of the 3 tested lincosamides delivered, like lincosamides antibiotics. Their conclusion that indeed this new antibiotic is very, very promising, especially for the treatments against their listeria diseases, and that if the bacteria is, even if it has the overexpressed factor, ABCF factor, or if this factor is by some reason is knocked out from the bacterial genome, this new antibiotic reveals that it's very valuable to treating their bacteria which has the resistance factor within its plasmid, encoded plasmid DNA as well. So I'm sorry, I'm a bit sick, so my voice might be not perfect. But yeah, this work was done between 3 different universities. It was within Harvard University, Umeå University in Sweden, and some experiment was done in Tartu University in Estonia. And just to take home message, Tartu University support Ukraine a lot, and especially Ukrainian students. It's also provide a lot of internship for the Ukrainian students, that you can come for some time and do some internship in Tartu University. So if you're interested, you can also check out their webpage. And thank you for your attention.
Дуже дякуємо.
На українській мові, так?
Так, можна, запитати українською.
Можна?
Так, можна. Мені просто було лекцію зручніше англійською вести, але так, звичайно, можна.
Перше, дуже дякую, мені там дуже сподобалось, дуже цікава була лекція. Хотіла запитати, чи вже використовували боксиміцин на людях, чи були якісь результати, і, ну, просто, можливо, є якісь, примірно, коли його планують випустити.
Ще й не використовували, тому що він ще знаходиться на стадії FDA approval. Тобто, зазвичай, щоб погодити новий медичний препарат, особливо в Сполучених Штатах, а розробники цього препарату саме з Сполучених Штатів, це триває 5-6 років. Цей проект почався в 21-му році, тому я вважаю, що, мабуть, ще 2-3 роки мінімум займе, щоб він з'явився як комерційно. Але він з'явиться комерційно спочатку в Сполучених Штатах. Коли він приїде до Європи, я не знаю. І на превелику шкоду я вже більше не працюю в академії, тому мені важко слідкувати за тим, як швидко він може з'явитися комерційно. Ось, але ще не скоро, на превелику шкоду. Ось.
Дякую.
Може від мене. Модне сьогодні питання, а як цей новий препарат впливає на біоплівку?
Гарне питання. Ми не тестували це проти бактерій, які активно виділяють біоплівку. Тому я не знаю, відверто можу сказати, але так як цей препарат, я можу I can think, я можу те, що так як цей препарат впливає лише на трансляцію, і він ніяким чином не корелює, як з клітинною стінкою і з біоплівкою, тому, мені здається, він не буде сильно впливати на розвиток біоплівки. Ось.
Окей, дякую.
Але я точно не знаю, це треба тестувати зазвичай.
Хотіла запитати ще, ви сказали, що після використання бактерії ще довго себе не проявляли, тобто до нього не планується, я не знаю, як це запитати, тобто не буде в найближчий час до нього антибіотикорезистентності, тобто мікробної резистентності.
На превелику шкоду це... Так, на превелику шкоду це залежить від того, як його будуть застосувати. Тобто, якщо його будуть застосувати, давати будь-якому пацієнту без виявлення штаму бактерії, без роблення антибіотикограми, то, звичайно, резистентність до нього з'явиться дуже швидко. Тому що навіть з тих даних, які ми отримували з MAC-тестів, коли була оверекспресія якогось антибіотикорезистентного механізму, то все одно ми бачили, що MIC було не таке низьке, яке б нам хотілося б. Тобто це було все ще в мікрограмах, концентрація була мікрограм and not нанограм, що зазвичай ми більш хочемо бачити в новому антибіотику. Тому, мені здається, це все ж залежить від його використання. Якщо його будуть не використовувати так широко, то тоді резистентність може не з'явитися так швидко. Ось.
Дякую.
Дякую. Скажіть, будь ласка, чи є питання до доповідачки? Якщо питань немає, надзвичайно дякуємо, що ви до нас приєдналися. Дуже приємно знову бачити вас нашою доповідачкою. Були у нас на першій нашій конференції. Це вже третя. Супер, надзвичайно приємно, що ви до нас доєднуєтеся. Сподіваюся, що на четвертій міжкафедральній конференції ми також почуємо від вас щось цікаве.
Так, дякую.
Де можна почитати, дізнатися більше про цей боксміцин?
Так, от...
Є дві статті, є наша стаття, наша стаття спрямована саме на вплив ібоксаміцину на листеріози. Але є ще стаття гарвардських колег, і там вже більш детально розповідається саме про синтез цього антибіотику. Я можу цю інформацію скинути Жені, і Женя може розповсюдити.
Хорошо, давай. Женя вам скине. Так, добре, я передам цю інформацію. Супер,
Добре,
дуже вам дякую.
Да, до побачення.
До побачення.
Так,